Hello, hello. Hello, everybody. Good to see you. Oh, wait, I don't know if you can hear. Good afternoon, Key. Thank you. All right, awesome. I'm assuming this means you can. Good afternoon. All right, good, good, good. I'm assuming this means you can hear me. Also, we're having a little technical difficulties here. Give me a second, but cool, cool, cool. Yes, good. Good afternoon, Key. Good afternoon, Samantha. Good afternoon, Juliana. Good afternoon, James. Good afternoon, Bree. Good afternoon, Valentina. Good afternoon, Michaela. Good afternoon, Christina. Good afternoon, Bradley. Good afternoon, Dante. Good afternoon, Panina. Awesome to see all of you. Okay, hello, Charday and Charday too. All right, awesome. Okay, bear with me for a second. We're having and hello. Oh, and good noon. Oh, that's interesting. Evelyn. Okay, it's great to see all of you. I'm very excited about. Good afternoon, Allison. Awesome, awesome. Okay, bear with me for a second because we're having a little technical difficulty with the board here. But what I, of course, well, yeah, just bear with me for a second. Okay, hold on. You right with I'm still here. You're still here. I appreciate it. Thank you for your patience. Be 2 more seconds. I think. I hope. Okay, this should work. We'll see. We're still there. Oh, and there's 2 more in the chat. Okay, we're gonna get rolling. Oh, okay, okay, okay. Oh, good afternoon to Weeba and wait, yes, and yes, anybody. Okay, there's things in the yes, anybody who has any questions that anything such as their grade or their midterm or any, certainly should hang out right after class today. And if there's a lot of people, we'll make breakout rooms. You know, if it's personal, we'll respect personalness. Also, if at worst, if we anybody who has any issues or concerns or anxiety or whatever, you should hang out right after class today. And at worst, we'll use that time to make an appointment for later or a phone appointment or something if that's what we have to do. But yes, I'm just addressing, there's some things in the direct chat. If you have any concerns of any kind, yeah, okay, great, great. But that's to everybody. Hang out after class, and at worst, we'll use that time to make an appointment. But I know it's but absolutely okay. And also I'll just say, I'm about to get the board going. We're about to get going. There are still some people that still haven't gotten their midterm back yet. I mean, the number is smaller and smaller, but there are some people. It's still not personal. I know it's um not convenient to say the least. Also, just to everybody, just want to remind you, because I'm aware that that's causes concern. That's part of the reason we're doing this thing where, just to remind you, um, that we are going to do this thing where whichever exam you do better on, I will weight more. So that's also sort of thrown in there, not thrown in there, but that's partly also just my way of acknowledging that if you've had to wait longer than is comfortable for your midterm, hopefully that softens the blow slightly of that fact. I mean, anyway, so give me a second. I think the board is working. But the main thing, you know, by the end of tonight or early tomorrow, I will post the practice that you will spend tomorrow doing in lab with Professor Talley, right? And then the real thing will be posted that night. You know the whole routine. Hopefully, if you have any questions about any of this, you should check in Google Classroom, or ask me right after class. But we still have the material to finish for the final. And I want to put up my board right now, but the material that we have to do today, or a big part of the material we have to do today, absolutely relates to the hearty debate that I understand you to have had today in the board meeting. My understanding is that you had kind of an intense debate. To my mind, that's fantastic. And it sounds like you had a debate on exactly like one of the deeper issues. Like from everything I understand from the 2 or 3 students that wrote of you that wrote to me, which I really appreciate, and from, corresponding with Professor Talley, it sounds to me like you got deep into the thickness of exactly one of the real right profound issues of Gauss's law. So of course I wasn't there. You may have found it very frustrating. You may have thought you weren't getting anywhere. I don't know how you felt, but I will tell you that you saved yourselves a lot of time and a lot of heartache by having that debate with one another today. You whether you feel like it or not, you just had a major study session. And I'll resolve the issues right here in like 1 second when I put up the board. And it's when I address the issues that came up today in the board meeting, which again, I'm delighted to do, I also want you to know they're not off the topic at all. Like they're exactly the issues that I would have been addressing today. So it's really perfect. So I don't know if that, so whatever you felt, I think those of you who are involved in that debate, I think you were doing the right thing, putting your energy in that debate. You were not bringing yourself backwards. You were not revealing yourself to be confused. You were revealing yourself to be wise and invested on a hard issue. And my last thing I want to say about that is absolutely is irrelevant who turns out to have been right or wrong or whatever. Like, don't even think about that for 2 seconds. Like for 1,000 reasons, don't even worry about it. If you were involved in the debate at all, you're right. Like literally. And any of you who did get very actively involved in that debate or sent me texts about it, also submit those for points, like for participation, please. Okay. So I'm going to hopefully make this board work right now. Bear with me for a second. I think it should work now. We'll see. But like, I couldn't be happier from what I've heard. And I'm saying that knowing that probably some of you thought it was a real bummer. I mean, just from historical experience, probably some of you thought it sucked, but and maybe it did in ways that I don't know. But it was, I never learned, well, anyway, whatever. I could go on all night about it. Anything I understand in physics now is because I engaged in major debate over the years with colleagues. Like I didn't learn in lecture. I learned what it is that I was supposed to learn. That's what lecture is for, to find out what it is you're supposed to learn. But then you learn it by banging your head against the wall with other people, generally your peers, like really. Okay. Or you learn it by having to fake it in front of a classroom for years and years and years, but that's another thing. Okay, here we go. Okay, here comes the board. That's good. Okay. Oh wait, someone else is here. So again, I'm going to just get straight to this material again, and because I've been trying to deal with these exams, which again, some of you still have not gotten back. I just want to keep acknowledging that because I know there's nothing I can do about it in the middle of class. Oh, hey, video. All right. Woo, that counted. All right. Thank you very much. That was points right there. A little bit of a tease, but again, now one last time. Hello, good to see you, Dennis. And again, if you still haven't gotten your exam back, you will. I will know that you will know that I will know in the back of my mind that put you in a bit of a hardship. I'm not saying I can like literally, turn that into a different grade but like, I'll know when you're on the borderline of something. I'll know, oh, that was a person that suffered a little bit, that had to wait a little bit believe me, I'll know. But they will come. And obviously I can't do anything about them in the middle of this class. So other than that, again, I'm going to say now in a minute, I'm going to get to the physics that we're trying to put together the next 2 days. My goal is to put together and close down this physics story for you. Of course, I know your goal is to emerge with a good grade. I want those two things not to be in conflict, but mostly I'm going to be focusing on the material. It will go a little fast. You may want to watch the videos over and over again, blah, blah, blah. The final exam will be shorter, like I keep saying, but the point of the final exam is to ask you to put together the point of all this material. All of this material actually leads to sort of a punchline, which is where we want to get to in these next you know, for whatever, this next 5 hours. So, okay. Oh, here. Oh, okay. Wait. Oh, and people letting in, but I know I'm always first on because I'm going to, wait. Okay. There's things in the chat. Hang on a second. Yeah. Okay. Something in the chat. Okay. I'm just going to say, I'm going to say, well, no, I won't. Hold on. Okay. All right. Yeah. So the two equations that are on the board, right? What I keep forgetting to say, what I keep trying to say is I'm going to try to be, once I start, the reason I'm sort of stalling a lot, because I always do, is once I get going, I'm going to be intellectual. Like I'm going to be about the material here, especially because I think the material gets really exciting at this point. I know the whole time that in your mind, you're worried about academics. Like I respect that. But just so I'm saying it's always true that if you have an academic concern, like grades or something, you can still put in the direct chat or you can wait till right after class. Like they will be addressed. But the best advice I can give all of you at this point for the next 2 days, whether you've gotten a midterm back or not, whether you think you're doing well in the class or not, like all of you, the best thing you can do is focus on the material that we're talking about. Like try to understand the material and assume that the more, pretend you're in your own private board meeting in your mind with this material, like debate it through, think about it, ask questions, whatever. But the more that you can conceptually try to follow this material, the more that will take care of all other issues. You focus on input and outcomes, as in grades, will follow. If you're thinking too hard about grades and skipping to that step, it'll be much harder to follow this material and you might get in your own way inadvertently. I can't put it any better than that, but that's been my experience at this stage of this course in past years. So the first equation right here on the top, which in theory, is what you got to at the end of the board meeting today. I mean, I'm going to back up on it in a second, but in theory, this is the issue of right now. And yes, this equation right here, which is very fundamental to physics, very, very foundational to electrodynamics, is called Gauss's law. No one's arguing that anybody proved it here in the class yet. What you ostensibly sort of did in the board meeting today is you started with one simple example, worked your way through the simple example, and then had a whole big argument about to what extent that example could be generalized to all cases. The claim, the ultimate claim, and I do believe that you got to this, the ultimate claim is that if you know how to read this law, it can be generalized to all cases. The big question that you guys were debating, I think, is like, can it really be generalized to all cases? Like all cases, period, or all symmetric cases, right? Which is a fantastic thing to be debating. Now, there's a lot of nuances to that debate. So you might even think you were wrong, and it turns out you were more right than you think, or you might think you were right, and blah, 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 blah. I'm going to break this all down. But this law on the top of the page, which is very important for our ending of the course, is a law. It's called Gauss's law. We're trying to argue our belief in it or our understanding of it from one simple central case. Okay. Then the law underneath it, you haven't seen yet, just to be clear. The law underneath it is where we're going to get to by the end of today. It looks very similar. It has a very similar structure, but you'll notice there's a B in there instead of an E, and there's a 0 on the right side instead of some other stuff. So that's where, and as a foreshadow or as a hint, that capital, just like that capital E in the first law, stands for electrostatic field. I guess just to foreshadow where we're going with this. This second law is called Gauss's law for magnetostatics. And the big capital B there will stand for magnetic field. That's where we're going with this. And indeed, the right side is a 0. That's where we're going. Don't overthink it right now, but that's like the goal by the end of today's class. So we can relate back to what you sort of saw or found at the end of the circuit thing yesterday. But right now, what I want to do is focus on this Gauss's law thing. I'm going to do my version of it a little bit quickly. Like I'm going to summarize what I think you did today in lab a little bit quickly. And then I'm going to lay out what I think the answers are to what I think was the debate that you had. Of course, I'm going to welcome questions or clarifications and stuff at that time. But bear with me for a second when stop me at any time. I'm going to back up. I'm going to do what I think Gauss's law says my way. I'm going to do it so you can see it properly. But I'm going to take advantage of the fact that you already did it today and therefore go hopefully a little bit quickly. Like, here's what I think your situation was. We had, and I do encourage you, please, even if you think you nailed it today, which clearly many of you did, just please copy this down nonetheless, because it's just fundamental, and I want to make sure we're all on the same page. What we have given here is a positive point source, right? A source, a point charge, which is the source of electric field, and it's positive, and it's called plus Q, right? Now we're going to consider a Gaussian So for starters, what you were asked to do today in lab, to be very clear, is you're considering, you're given some point source. So even though this was in our heads, even though this is a thought experiment, what we're thinking is that we're imagining that there actually is like a proton sitting on a lab table or in outer space somewhere, right? So it's a thought experiment, but we're thinking about it as though it was an actual experiment. There's an actual proton sitting, or an actual point source called plus Q sitting somewhere on a lab table or in space or whatever. And then we're imagining a sphere surrounding that point source, a sphere of radius capital R centered at the point source. Now, I want to be very careful about this. Like, the whole thing is imaginary. It's all in our heads, right? But we're imagining an actual real charge. But then we're imagining that we, in our minds, draw a sphere around that charge. So we don't think that there's a glass ball in the lab or a metal ball or anything like that. I want to make that distinction. We're considering a hypothetical region of space known as a sphere surrounding that charge. Okay. And I see there's something in the chat. I'll get that in 1 second. And since you've already done the board meeting, I'm going to use the benefit of hindsight, or like Monday morning quarterback or whatever. And I'm going to say, whenever we consider or imagine or hypothesize some kind of closed surface around some bunch of source charges, we call the imagined closed surface a Gaussian surface. Now, we wouldn't have known to do that if we didn't already know that this whole thing relates to something that we're going to call Gauss's law. But like, now you know that from today. So I'm going to say from now on, whenever someone's like walking to a lab and is like, oh, there's a proton there, or there's an electron there, or there's a hydrogen atom there, or whatever, and they want to ask questions about the field created by those source charges, the technique that physicists and mathematicians use in order to predict or compute the field in the surrounding regions is they will consider or hypothesize what we call a Gaussian surface. A Gaussian surface. In fact, I'm going to say this right now. And I know there's something in the chat. Bear with me for a second. Oh, God. Oh, if my tablet runs out, that would be a disaster. All right, hold on one second. There's like a battery issue here, but it's plugged in. Hold on. Hold on. Okay. Um, uh, in fact, I know there's something in the chat. I want to get this clear. This is something that would not have come up today in the board meeting. Okay. Remember, so bear with me for a second, a little terminology here. Remember at the beginning of this course, we talked about integrating along paths. Path is like a one-dimensional region of space, right? But then we introduced this idea of a closed path at the beginning of this course. And we even introduced the idea of an integral with respect to a closed path. We called it a closed path integral. What was a closed path? A closed path was still a one-dimensional region of space, but it was a one-dimensional region of space that automatically constituted or eventually constituted a round trip, right? A closed path was a path where a closed path was a path that allowed you to, if you were a little particle in that path, you could keep going always in the same direction. You could never change your direction, and yet you could end up where you started, right? Like that's what a closed path is, like a ring. A ring is a closed path. Well, so there are paths that are open, like line segments or lines or rays, and then there's paths that are closed, like rings. Same idea we have in 2 dimensions. A two-dimensional region of space is called an area or a surface, right? Now, again, just bear with me for a second. A two-dimensional region of space is called an area or a surface. Here, let me change the view on the screen. This, this is a two-dimensional region of space. I think like this square is an area or a surface, right? It's the total amount of space occupied by this piece of paper is measured in square meters, not in meters, right? But it's what I would call an open region of space, as opposed to if I touch its 2 ends together, you can't really see this now, and especially if I closed it all up, if I even put caps on the end, then it would be a closed region of space, right? In that there too, you could walk and walk forever and eventually hit where you started, right? Now, closed areas or closed surfaces are still two-dimensional regions of space. But back up for a second. Now, again, I know I'm saying something conceptual here. But with a closed path, notice a closed path is still a path. It's still measured. It's the region of space that a path occupies is measured in meters, not in square meters. And even if you close a path up and you make like a ring, what do you have? You have like the circumference of a circle, right? The circumference of a circle is a line that's been bent into 2 dimensions. It's warped, it's distorted. is forced to occupy two dimensions. You can't bend a line and touch its ends and make a closed line. You can't do it unless two dimensions exist, right? But the closed path is still a region of space that is itself one-dimensional and measured in meters. Like the circumference of a circle is 2 pi r. It's not 2 pi r squared or something like that, right? Perimeters and circumferences are lengths that wrap around or bound open areas, right? Now, similarly, I just want to get this out there before we go any further. Similarly, a closed area or a closed surface is still a surface. It is still a two-dimensional region of space, but it's warped, it's bent. It forces us to believe it can't happen unless there are three dimensions of space within which to work, right? Again, I just want to lay this down. Okay, I said that already. So I'm saying the hallmark of a closed surface is that it creates a situation where we definitely have an inside and an outside. A closed surface is the boundary to a unique volume, right? Like the surface area of the globe is the skin of the globe. It's the boundary of all the thick bodily three-dimensional voluminous globe within. The surface area is still two-dimensional, but it's the boundary, it's the outer layer, it's the enclosure of the volume within. I'm going to just summarize this. Now, again, before we even get into everything you did in the lab, just notice this. This is what I'm saying. A closed 1D region of space is the boundary for an open 2D region of space, right? I'm backing up now. I'm trying to make an analogy here. I'm trying to bring elements of the course together, you see, right? Like a ring, right? Or even like here's an open two-dimensional region of space, this piece of paper, right? But what's the boundary of it? What's the distinction between it and the rest of the world? Well, it's the edge all around, the perimeter, right? The perimeter of this rectangle, the perimeter, like L plus W, or I'm sorry, like W plus L plus W plus L, right? That's a certain number of meters. The closed path is the closed one-dimensional region of space is the boundary for the open area, the open two-dimensional region of space, right? And similarly, I just want you to write this down, just have this as a way of understanding space, because ultimately physics is about space and time, right? So similarly, a closed 2D, sorry, that's illegible, 2D region of space is the boundary. And when I say boundary, I mean like the distinction between the region and all the rest of the world, is the boundary for a unique 3D region of space. Unique, now that's a different word, meaning, and I'm going to tie back to what you did in the lab today, but like if we have like this dot, this plus Q, right? And then we surrounded it with a spherical shell, which is really what we're doing. We're imagining like the skin of an orange or the surface area of a globe, like surrounding this point Q. That is a closed area we're imagining. It's still an area. It's still measured in two dimensions, and it's still subject to the whole idea of flux, right? It's still an area, but it's a closed area. How do I know that it's a closed area? Well, by this way of talking, I can tell that it's a closed area because it's the boundary to a unique, like a one and only, an identifiable volume inside, meaning the volume of that sphere. Like I can tell the difference between anything that's inside that sphere that is enclosed by my closed surface versus anything that's outside. What, right? So once you close up a surface, you make a very definite volume inside, which is like distinct from all the rest of the volume in the outside world. Okay, I just want that to have that. Now I'm gonna. So we've done that. So our setup for the situation you did in the board meeting today. I'm just gonna draw it again. Then I'm gonna look in the chat. I know there's something in the chat. It was probably super important 5 minutes ago, and it's probably totally irrelevant now. But probably like someone saying that their hair is on fire, but the fire will go out, and I know an answer. Anyway, so I just want to make it clear before I go any further, or I'm trying to make it clear that like we're imagining a surface, a region of space surrounding this plus Q, and then our question is, or the question that you already answered today in lab, which I will do quickly. The question is, compute the net flux out of the spherical shell of radius R centered at Q. So again, the question that you asked today was how much electrostatic field would be flowing through this imagined region of space outside the actual real charge. So we're asking about what's happening through this region of space that we're considering in our minds. And one last thing, one convention that we always use in electrostatics is anything that fluxes out, we always call positive, and anything that fluxes in, we call negative. Now, there's no such thing. There's no obvious out or in if you just have an open area, right? But once you have a closed area, the whole thing that I was just saying is once you have a closed area, there's a definite distinction between what's inside and what's outside. So anything that's going from inside to out, we count as positive. And if anything were coming in, we would subtract that and call it negative. So that's why I say we're going to compute the net flux. Okay, so that's the project. That's what you were asked to do today. This is what I'm going to whip through maybe in a minute. But first, the chat. I even have a feeling I know who. Let's see. Oh, sorry. What's the word before? Sorry. All right. I knew I should have. Oh, there's a lot in the chat. I'm sorry. One second. So the word after. Okay, let me back up. Okay. The word after, so back on this first page, the word after hypothetical is sort of unnecessary. It's the word mental. I'm just trying to emphasize that these Gaussian surfaces that we draw, they are a construct. They're a technique that we think of in our mind in order to do computations and predictions. Any of these closed surfaces that we're talking about, they're in our mind even more than the charge that's in our mind. I don't know if that makes sense, but even though everything we're talking about is in theory here, like we're not literally seeing a proton in the lab, we are imagining that we see a proton in the lab. But then we're imagining that we imagine a surface around that proton. That's what I mean by the word mental. I don't know if hopefully that makes sense, but okay, so that's that question. What's the word before plus Q? Oh, it just says called plus Q. So I'm saying there's a positive point source called plus Q. I don't know if that helps. So, okay, and then to clarify. Okay, to clarify something discussed, and I love any question about today is great. I mean, I'm going to do this no matter what, but the questions help me. To clarify something discussed today in relation to flux and Gauss's law, do the surfaces in question have to be 3D as part of the necessary appropriate conditions? Okay, that's actually a great question. Maybe I just answered it, but maybe not. So someone's asking in direct chat, do the surfaces in question have to be 3D? So here's the thing. Surface necessarily actually means 2D. The surfaces, and I don't mean that condescending, like this is subtle stuff. All these surface, let me back up. Anytime we calculate flux, we are calculating amount of electrostatic field through an area. Like by definition, flux is stuff going through an area. And the word surface is interchangeable with the word area. I use them interchangeably. Flux is all about field lines going through areas or surfaces. Surfaces and areas are both two-dimensional regions of space, like measured in square meters. However, the reason this is a really good question in the direct chat, and because this gets confusing fast, is flux is a concept that applies to any kind of surface, any kind of area. But there are two kinds of surfaces or area. There are open areas or surfaces, and there are closed surfaces or area. A closed surface or area is still 2D in terms of its size, in terms of how you measure it. A closed area, and I want to, and if anybody understand, whether it's the person who asked me this in the chat or anybody, I want some feedback in the chat. If once I say this now, if it's landing with you or not. A closed surface is a surface. It's a two-dimensional region, but it's one that's bent into the third dimension and then like wraps around and touches itself so that at the end of the day, it contains or it encloses a three-dimensional region of space. A closed surface itself is definitely 2D and has to be 2D for us to talk about it. But a closed surface does contain or enclose or bound, act as the boundary for a three-dimensional region of space. Slight sidebar on that. In English, if you weren't in a physics class right now, if you were just like in English, you may have noticed in your life that people sometimes talk about surface area. They'll talk about the surface area of planet Earth, or they'll talk about like the surface area of like some car that you're trying to paint or something, like an igloo that you're painting, right? You've heard the word surface area. Now let's stop for a second. Surface and area both mean the same thing. Why does anybody ever say surface area? It sounds redundant to the point of like silliness, and your brain probably just like accepted it or whatever. But whenever people say surface area, what they're actually trying to say is they're saying the area of some closed surface. When people talk about the surface area of planet Earth, they're talking about the area on top of planet Earth, and they're calling it a surface area because they're saying it to make sure that somehow their brain understands that it's an area that's bent and warped and wrapping around the volume of Earth. What we call in physics closed surface or closed area is what like English people often call surface area. Okay, but I'd rather use our language for a number of reasons. But so to answer your question, anything we do with flux could deal with either kind of area. When we talk about flux, the definition of flux applies to any kind of area, open or closed. But whatever we're going to ultimately infer or say about Gauss's finding, Gauss's law, we're about to be interrupted. Whatever we say about Gauss's law specifically only deals with closed areas. 1 second, please. And you could tell, just 1 second, you could tell, I'm not going to flip the pages now because it'll confuse people, but when I originally gave the definition of flux, like yesterday and the day before, the definition of flux has a double integral, right? Has a double integral, but then just hold on a second, please, sorry. But then when I'm making a, wait, please, hold on, just please. But then when I'm making a statement about flux known as, please, just 1 second. When I'm making a statement about flux called Gauss's law, you'll notice I put a circle on the double integral. That is very important. It's not a typo. And it's not a typo that it's missing from the definition of flux. Flux can apply to any surface at all, but Gauss's law is making a claim only about closed surfaces, which are those ones that warp around 3 dimensions of space. Now 1 second. Okay, yes, I probably am. Okay, what would you like? Sorry.
Regular switches?
Plugged into the
dock? That's your switch.
Well, you have both switches in the room. You have the blue switch light and switches.
Oh, thanks, Dad.
Thank you. Okay, sorry. Okay, so that's and if he may be right. If I'm talking too fast, I mean, I probably get more flustered when he comes in. But if I'm talking too fast, let me know. Seriously. Okay, is it okay? Yeah. Yeah. I'm not sure. Yeah, someone's asking. I think yes, it's okay to SS the writing because I can't type right now. Yes. Okay. Oh, okay, great. Thank you about the thank you. That makes sense. Okay. Wait. Okay. 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 So last thing in the chat. Now, these are great questions, and even if I sound all frantic, it's because I sound this way. But you should keep these questions coming. And even if I say something about your question directly to you, like even if I say it's off, whatever, you can't know until you try. So yes, to the last person who put something in the chat, Gauss's law, the thing that supposedly you found at the end of the board meeting, and that supposedly I'm going to find, with you in a couple of pages right here, the Gauss's law result only applies to closed surfaces. Like, yes, it only applies to closed surfaces. Like it. So in fact, okay, I'm just gonna. I guess I'll write this one more time. I just want you to note again. We're gonna get back to it, but well, we're gonna see right now. All right, we'll see right now. Our setup, the setup you have at the lab today is you have this point charge, and you're going to get the flux through a sphere, through the surface of a sphere surrounding that charge. And one point charge at the center of a sphere is kind of like on purpose the most fundamental, simple example we could possibly construct. And it's not because you're students, or it's not because we think we're dumb. It's like the first example that Gauss ever did. It's physics is always like building from building blocks. But the whole idea here is that if we can see from this example how to compute flux in this simple case, hopefully then we can see how to use flux in more complicated cases, and maybe even find out something powerful about flux in more complicated cases. So our goal here is to find the flux in this situation, right? Let me remind you right now. Well, okay, so what did we do? What did you do? Well, step one. So I'm solving now. Okay, so all right, to solve. I won't say step one because I don't mean in the 5 steps. To solve, first, draw the field lines for the situation. Okay, this is why we spent so long talking about field lines yesterday. Do 2 plus Q. I don't know why I'm writing this in red, other than I'm going to put the field lines right in the picture in red. And I know you did this in lab today, but the field line diagram here, I'll even say, pick scaling, just like we did yesterday. Pick a scaling factor of 8 lines per each Q. Okay. Then we only have one Q, so I'm gonna draw 8 lines. And the whole idea, remember, even though we've already seen this picture before, I'm following the rules. The rules say you pick a scaling factor, and then it says only start your whenever you have a positive, that's where field lines begin. And we don't have any negatives, so no field lines are going to end anywhere. So, and it says you're supposed to draw field lines as symmetrically and smoothly as you can, assuming that you follow all the other rules. So since I just have this one dot, the most symmetric arrangement and smooth arrangement of 8 field lines that I could have coming out of a positive would look like this, right? This is the field line picture from a point charge, and the field lines go on forever, right? Notice, like, there's no other negative. So those arrowheads are not landing on negatives, and they're not ending in empty space. The whole idea is they're just going to the edge of the page. They're going on forever. Most specifically, they don't end at the spherical surface, because the spherical surface is just a shape in my mind, right? Like there's no reason for those field lines to end just because I'm imagining a particular radius. So they go on forever in this cement. That's the field line picture, right? And that's what you always do first with any Gauss's law problem or any electrostatic problem. So I've drawn the field lines. Now I'm being asked to compute the flux. Now, again, I know you already did this, so I'm going to try to speed up in a second, but I want to take this opportunity to address some of the private chat questions, because second, write down. So if I were doing the 5-step, problem solving method, like I wrote the diagram, I wrote the question down, which is compute the flux. So now I'm going to step 3, GDP. What are my general definitions and principles? Well, the general definition here is the definition of flux. Like that's what I need to do this. So I'm going to write down the GDP, the definition of flux. So the definition, and this is where I want you to note something. the definition of electrostatic flux, the thing I'm being asked to compute, the definition is this. That's the definition. So no, those of you who are asking these great questions in the chat, please note, I mean, I wrote this yesterday and the day before. That's the definition of flux. It can look intimidating. Yes, it's a double integral of a dot product. I mean, that's why we sort of practiced integrals and dot products at the beginning of class. You sort of do have to get used to them. But the way to get used to integrals and dot products is the same way I did. Remember that we do a lot of this complicated math in order to handle a lot of complicated varying cases. But when in doubt, first think of the simplest case in your mind. In short, what that double integral of the dot product of E times ds means is just total amount of E field times area, right? The integral means we're taking into account that this might be a big situation with lots of variety in it. So we have to handle it subtly with an integral. But it's just saying, take a step, ask how much the electric field is at that, take a two-dimensional step, like step on a tile, ask how many field lines are going through that tile, multiply the two together, put it in your bag, step to the next tile, ask what the E field is there, multiply by the size of the tile, put it in your bag, walk to the next tile, right? We're just adding up a bunch. An integral is always a continuous sum of products. The product here is E field strength times size of area. It's an infinitesimal. Oh, sorry. Is that someone? Oh,
I have
okay.
a question.
Oh, yeah. Okay. Sorry. Yeah.
It's perfectly fine if we write the formula double integral of E field times dA. Is that also acceptable?
Oh, yeah. I'm sorry. Sure. Yeah, absolutely. You could call it A. A lot of textbooks and websites call it A. A is totally fine. I don't use A just because we already have A for acceleration and because this. But yes, either one's totally fine as long as you know. I use S for serve, but yeah, totally. Yeah. Absolutely. Right. Okay. So the fast thing I'm trying to say to everybody is notice, yes, this is a double integral, which just means it's an integral times an integral. It means it's a two-dimensional integral, right? Don't let it intimidate you or whatever. And technically, maybe I don't even have to, I mean, the ds is already telling you that the variable of integration is an infinitesimal element of area. Like it just means that the steps we're taking, the little bits we're doing are area bits. Let me also remind you before I go further, because of course you're going to see this. I mean, of course, integrals, I know in my heart that to many of you in your heart, you see an integral and you want to vomit. Like I do understand that. But another way to understand integrals is just to take it to the limiting case and remember, like what we're going to find here is an integral is only necessary when things are varying. When things are constant, when, in this case, the E field doesn't vary from step to step, then this is just a fancy way of saying multiplication. It really is. We're just saying it's the total amount of electric field times the total amount of area. That's what we're saying is flux, everybody, okay? That the definition of flux is E field strength times area. But the thing I want to drive home right now before I go any further is notice that definition does not have a circle, does not have a circle on the double integral. This means that the concept of flux applies to any kind of area at all, whether the area is open or closed, right? That's not a typo. That's the definition of flux. That's what we're about to grind through right now, or what you already ground through this morning. Okay, put something in the chat. Sorry. Well, I'm just answering chat. Okay. 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 So what you guys did today, I'll try to do a quick, I keep saying I'm gonna do this quickly, but I keep lying to myself. All right, so we apply the definition. So we say the source is a point source. So we know, and I know you know this, so we know that the E field function is this. And remember, we originally wrote that whole constant as a K, but then we started writing it in this fancy way, which was annoying at first, but I think you saw today in lab why we write it in that annoying way. Wait, and there's something in there. So we're going to do the integral just like you did, right? We're going to plug that in. So we've got 1 over, I'm doing this. And again, I'm sort of assuming that you already did this, but stop me if, so we plug that in for E, right? And then the whole thing is supposed to be dotted with ds. But as I think but remember, the dot product in general, right? If you have two vectors, A and B, of arbitrary length and arbitrary direction, and if they're separated by an angle theta, the definition of dot product is the magnitude of one times the magnitude of the other times the cosine of the angle between them, right? The whole idea of dot product is that you're multiplying the component of one, which is parallel to the other, times the other. You're only multiplying parallel components. You're measuring the extent to which two vectors are actually lined up. And that's how you can get a dot product is the scalar product. It's the way of multiplying two vectors that produces an answer without direction. It's the way of multiplying two vectors that gets an answer, which is a non-vector. How can we do such a thing? Why are we allowed? Because what we do is we treat the two vectors as though they are just numbers on the number line. We only multiply the component of one vector that is already on the same number line as the other vector. Cosine of theta ensures that, as we said earlier in the semester, as you saw in the homework earlier in the semester, because the whole, like cosine always returns a fraction. It's like returning a percentage. If theta is 0, that means the two vectors are perfectly parallel with each other. Cosine of 0 is 1, right? So when you dot product two vectors that are perfectly parallel, you basically take the length of one times the length of the other and then multiply that by 100%, by 1, i.e. 100%. You say we're taking into account all of both the vectors because they're both right on the same number line. On the other extreme case, if two vectors were perpendicular, the theta between the two would be 90 degrees. I mean, right, if they're perpendicular. So the cosine would be 0. So no matter how long each one was, if they're not at all parallel, then the dot product would return length of one times length of the other times 0. You get no, right? So anything in between is some percentage of their lengths gets multiplied. The more parallel they are, the higher percentage of the scalar multiplication gets returned, right? So that's what dot product does. So, and you also remember that as complicated it was, r hat, the new thing for all this, literally just meant r vector divided by r, which meant that the length of r hat, the unit vector r hat, the length is always 1. Right? So, going to the next page, and again, hopefully this is familiar to what you did today or something like this. So I'm right now, in other words, I'm looking at this integral that we are being asked to solve. That integral looks like a mess. I mean, I am intimidated by that integral. If I were almost any of you, I'd be like, are you kidding me? I'm supposed to do that? But yes, because if you take it step by step, if you break it down piece by piece and you don't lose confidence, you realize at the end of the day that it is actually much more solvable than it looks. I'm going piece by piece. First, I'm just looking at the dot product part of it because, frankly, those vector symbols are intimidating. They look like they're clogging up my system. I don't know how to deal with an integral with vector symbols in it. So first, I'm just looking at the vector aspect. I'm looking at that I've got the dot product between a unit vector and another vector. So I'm just following the rule of dot product and saying, oh, so I'm just recopying everything else. Right, but then, so I'm recopying the whole thing, I guess. Here, I recopied, right? But I'm trying to do that dot product at the end. What is that? Well, that means 1 times Well, I'll do it. Well, yeah, it means 1 times ds times the cosine of the angle between them, right? That's what it means. And why 1? Because the length of r hat is 1. And why ds? Because the length of the ds vector is ds. So what we have so far is this times, so I'm going to leave out the 1, so times ds. Now cosine theta. Now what is theta? Theta means the angle between r and ds. What is ds? ds is any little bit, any infinitesimal bit of area within that whole surface area that we're talking about. ds is a bit, it's an area element of the spherical surface that we're imagining, the Gaussian surface. So like here would be a little bit of ds. I can't, you see, this would be ds right here. Okay, right? That's the area. But why is ds being called a vector? Because we said yesterday, in order to picture and deal with or track the orientation of some area, we picture a vector sticking out of it, perpendicular to it, because it is not a vector, it's a bit of area. So we picture like a flag, like an arrow sticking out, and however the whole area twists, the whole arrow will twist, so it can track the orientation of the area for us. The only thing is it's always off by 90 degrees, like it's sticking out perpendicular to that area. So if the vector ds, let me try to draw this clear. The vector ds would be sticking out perpendicular to the surface cut out from that Gaussian spherical shell. If that's what ds is, then I'm claiming to you right now, and this is a part hopefully you already worked out in the board meeting, I'm claiming to you that any ds I pick, and this is on purpose, this is why we picked a spherical shell centered at the point charge q, at the point source, any bit of area that I look at that spherical shell, at the surface area of a globe, any bit of area I pick that has an arrow sticking out of it perpendicular to it, like any flag on the surface of the earth, is necessarily parallel to a radial line drawn from the center of the earth to that flag, right? Like, in other words, if there is a field line right here, just not one that I drew, that field line is necessarily, or that radial line, or r, whatever, any radial line is necessarily perpendicular to the area, meaning parallel to the ds vector that represents that area anywhere I go. In other words, theta is 0 necessarily, no matter where I look on that surface. And that's why I picked that particular surface. So I'm saying theta is necessarily 0. So cosine is 1. So the vector so we don't have to take any funny cosines or anything. It's a full body dot product everywhere, which is good and not coincidental. So now I've gotten rid of the vector symbols. I have this, right? And I didn't just like ignore them. I've literally worked through the vector symbols. They're now gone. This is now my integral. It still looks intimidating, but as you found today in lab, ds is the variable of integration. The variable is s, or if you want to use a, you can use a. But what does it stand for? It stands for a bit of surface or a bit of area. It's a two-dimensional integration variable. That's why there's 2 integral signs on it. So that's the variable. Everything else before it does not contain that variable, symbolically nor physically. Like, in other words, Q is definitely a constant, 4 is definitely a constant, pi is a constant, epsilon naught is a constant. But even R, that you might think, wait, isn't R some kind of variable? Yeah, R is some kind of variable, but it's not the variable at hand. R means how far away are we from the center. ds means how big a chunk of the area are we talking about. That is 2 completely different issues. And the truth is, no matter how far out we are, that doesn't affect what part of the area we're looking at, or vice versa. So, as I think you said in lab, and obviously put in the chat if you did something differently or if you disagree with it, but I don't think this is where your disagreement was. So I should go fast. So I'm taking out and this is the way this works. All mathematicians and physicists get more and more used to integrals and things that look hard by doing ones first that turn out to be easy. Okay, well, anyway, so all of those things come out. It's still the rules of integration. So we're left with all that stuff times double integral of ds. Well, just like the integral of dx. Well, I don't want to pause. All right, I'm going to just say this. You don't have to put in the chat, but just think for a minute. If I wrote, what's the integral of dx? I believe many of you, if you're still paying attention to me, would know the answer is x, whatever x stands for, right? The integral of dx, whether you want to call it the fundamental theorem of calculus or the power rule or whatever, integral of dx means add up a whole bunch of infinitesimal dx's until you get the big total x, whatever x stands for. So the integral of ds means add up all of the little bits of surface area until you get the total surface area. So what we're saying is, this flux, and we're almost there at the conclusion that you got today, we're saying that the answer to the flux, now notice the really intimidating integral is now not so hard to do because I'm able to take so much out of it. If you're thinking, well, okay, great, but what if I had an integral where I couldn't take so much out of it? Very good question. But the whole point of this whole procedure that we're learning the whole point of this whole procedure, the procedure's designed. The reason that we're all of a sudden talking about flux, which seems like a very obscure thing, is it's designed to create situations where all the integrals that we would have to do, we're on purpose setting up integrals where we can always take stuff out of the integrals and make the integrals easier than they look. Like, that's actually the purpose here. So don't worry. If you get into a situation where you can't take a bunch of constants out of the integral and make the integral like much easier to do than it looks, then you're actually doing something wrong physically. Honestly, what's happening here is we're using physics thinking in order to reduce mathematical computation. So anyway, we have this, right? This is what we have so far, which we're saying is the same as I'm just writing in English to make it clear. Like, technically, the integral of ds is s, right? But what does s stand for? Surface area. And that's redundant, but, the closed surface, right? And of what? Of, in this case, the sphere that we drew. Like, the surface area, the spherical shell bounding a sphere. It's so this goes back to one of the direct chat questions. This is a two-dimensional concept. It's a closed surface, but it is a surface. Total, and as you know, total surface area.
Sorry.
Oh, sorry.
I know you said it earlier, but it kind of slipped me, and I'm trying to think about it and I can't. I know you said the double integral, when we have it, it means it's kind of like a continuous. I'm probably not choosing the best word, something like continuous or something like that. It's not necessarily us taking the integral twice, is it?
It could always be thought of taking an integral. If an integral in the strictest terms, if a single regular everyday integral, if the idea is that you're walking along some x-axis and every step you take asking what's the value of the function, like for a regular integral, if y equals a function of x, the whole idea is of the integral of like y, the integral of f of x dx means you picture yourself walking along the x-axis, walking along the independent variable, and every step you take, you ask yourself, what's the value? So every input step you take, you ask yourself, what's the value of the output? And you multiply the output by the size of the input step you just took. You multiply them together, throw them in your bag, and then you take the next step. In other words, this is why regular integrals, when you first learn about them, you can think about as like the integral of some function is the area under the curve, meaning you can picture it as a bunch of rectangles under the curve, because each one of those rectangles is representing that you took a step, like the width of the rectangle is you taking a step on the x-axis, and then the height of the rectangle is how much what the value of the function, the output is that got returned at that step. So you multiply your step by the value of the function, you multiply dx by f of x, and then you add up all of those products, and the whole sum is what we call the integral. Like, so the integral is the continuous sum of products of output times input. So in a strict, and that's what an integral always is, if that helped anybody. I hope, like, an integral is always the continuous sum of the products of the input and the output. So in the strictest terms, an integral is always asking us to picture ourselves walking along a line and asking what's happening as we walk along that line. So strictly speaking, if now, when we're talking about double integrals now, the way a physicist pictures them is, okay, instead of taking steps, like instead of taking one-dimensional steps along a path, we're now stepping on tiles. We're like not stepping on a centimeter and then a centimeter and then a centimeter. We're stepping like square centimeter, square centimeter, square centimeter, asking the value of the function at each of those square centimeters. So in a physicist's mind, we're sort of doing it all at once. We're calling the variable of integration ds. We're doing it all at once in just like one big two-dimensional way of thinking. But to answer your question now, honestly, they're like, reason they even work, the reason we're even allowed to do them is that you could, if you ever wanted to, you could break down the whole thing and say ds itself is just shorthand for like dx times dy. And what we're really doing is walking along an x-axis, asking what the field is doing, throwing it in our bag, walking all the way down the x-axis, getting all of those values, adding them all up, and then making a right turn and walking all the way along the other axis and doing it again. So honestly, I think this answers your question, like a double integral, like we believe that they're valid because you could always break down a double integral into an integral times an integral, like a length times a width, and then get one big result for that whole area. You can always like sort of prove that it's equivalent. And if it makes, for anybody, mathematician or physicist, if it makes it easier to picture it that way or to break down the procedure that way, it always is valid. You could always think of a double integral as an integral times another integral. Or in these cases where we kind of know in advance that stuff is going to keep coming out of the integrals and we're not going to like actually, the computations will always look hard, but they end up being easy, which is the whole physical point here. So in my mind, we don't have to think of it that way. We could just think of it as I'm stepping on a tile, stepping on a tile, stepping on a tile. Does that answer your question at all? Or is it too much? Oh, wait, I'm looking. Did I just lose? I feel like I mean, it was a great question. Wait, did I just?
You confused me more. I'm not gonna lie. You confused me more.
All right, no, I appreciate the honesty. All right. So wait. So no, I appreciate the honesty because it is. So let me back up first. Let me simplify. The actual answer to your question is, honestly, a double integral can always be viewed as one integral times another integral. It can, if that helps you. It always can be viewed that way. But if you don't like that way of looking at it in physics, in this context, you never have to. You never have to look at it that way. And the only reason I'm even drawing the two integral signs is to highlight the fact that our variable, like it's almost redundant. If you really understand that the variable of integration is what I'm calling ds and you're calling dA, if you really understand that bit, like that infinitesimal input element is 2D, that's the important thing that we're trying to get across here. And some textbooks won't even draw it as a double integral. They'll just write the integral symbol because they are thinking in their minds that concept's already taken care of by your choice of D. So maybe I'm confusing you again, but I am saying it's a two-dimensional integral, but you could think of it all at once. You don't have to break it down into two integrals if you don't want to. Maybe I'm really not understanding the question. You want to give it one more stab or should I go? Do you want to just repeat your question? Because I feel like it's valid, and if I don't want to make it worse.
No, I was just asking, what does it mean by the double integral? But you explained it earlier, you know. You explained it earlier.
Okay, the double integral
earlier in class.
Okay, the double integral just means that this is a two-dimensional situation. It's emphasizing that this is necessarily a two-dimensional situation, not a one. It means absolutely what we're talking about is walking throughout an entire area, not just walking along a path. We're walking through. Okay. All right.
Okay.
Very cool. Very cool.
Thanks.
Thank you. Thank you also. And thank you for your honesty. Okay. Okay. So now, so like the variable of integration is ds. That means a little bit of surface. The total amount is the total surface. Total surface of what? Of the region that we're looking at. We've been asked to get the flux through a particular surface. Like flux is always, I'm talking to everybody now. Flux is always a question that is asked of some particular surface, some area of space. Again, I don't care whether you say the word surface or area. They're the same. But it means a two-dimensional region of space. So flux is always asking about what's the field through some two-dimensional region of space. In this case, the particular question that you were all asked in lab is, due to this one point source, what's the total flux through this particular region of space? The surface area of a globe centered on that charge. Again, it's like imaginary, but we're asking like how much, what we're really asking is, what's the field impact on this surrounding region? If you put a proton in a lab, I'm claiming with fields and field lines and all this stuff that the proton affects all of space around it. What we're really asking right here is, well, how much does it affect this space around it? Like if I added up all the field strength, all the newtons per coulomb waiting to happen in this region, what total number would I get? Like that's what we're asking here. It's very much, notice, okay, I'm going to take a risk here. It's an integral of a dot product. It's very much non-coincidentally like what we do in early physics when we learn about forces, but forces act on points. So then we back up and we like squeeze every bit of knowledge we can out of free body diagrams and Newton's laws and all that. Then we back up and say, but hang on, what if a force acts through space? What if a force acts along a path? How much accumulated effect does the force have throughout a path? So we do the integral of the dot product of force times path. We call that work, right? Work is the accumulated effect or consequence of a force throughout a one-dimensional path. Now we're doing something very similar. We're saying we got this field idea now. Fields go everywhere in space. So let's look at the accumulated effect of field throughout a region of space, like a cross-section of space. It would almost be like saying, I'm shining a bunch of light out of a pinhole or out of a bulb. I want to know the effect of light on the surrounding space. So what do? I put a screen. I put a screen up and I look at how the light bounces off the screen or creates shadows or whatever. I get a cross-section of space. In other words, light goes everywhere in three-dimensional space. How do I look at its effects? I get a cross-section of space with a two-dimensional screen that might be bent, depending on what I want. And that's what we're doing here. We're looking at a two-dimensional closed surface area of space, asking what's the effect of field on that area. Well, we chose the surface area of a sphere. The total surface area of a sphere is always 4 pi r squared, like assuming a sphere of radius r. Right? This is just from geometry. It's also from calculus if you really think about it. If you take the derivative of that, if you take the integral of that, you get 4/3 pi r cubed, which is the volume of a sphere. And if you ever think about like the circumference of a circle, it's 2 pi r. But if you take the integral of that, you get pi r squared, which is the area. Oh, wait, what? What's he talking about? Don't even ignore me unless you don't want to. But yeah, it all fits. The point is, this all fits together in the end. But anyway, the surface area of a sphere is 4 pi r squared. So that's what I plug in there. I'm saying then that the flux, at the end of the day, in this example, the flux, right, after all the math I did, notice this, even if you've gotten lost in if any of us have gotten lost in some of the details, the dot products, the integrals, at the end of the day, I'm basically saying here is E and here is area. What flux means is total amount of field times total field strength times total area, right? We have to take into account integrals if the field strength is changing. If the field vector is changing in either magnitude or direction as we look throughout the area, then we have to be really careful about the integral. But it turned out here, we specifically picked an example where the field strength and direction, the angle and the magnitude of the field vectors, the field lines, were the same everywhere throughout the surface of that sphere. So the integral became trivial. And then, as you found today in lab, and we're almost there for good or for bad, you found, oh, these 4 pi's cancel, which is why we write the constant that way to get this convenience. And oh, even more importantly, the r squareds cancel. So what you found today, now we're almost at, you found this. Right? So the first thing you found in this example, in this case, the total flux does not depend on size of sphere, right? Let's dwell on that for a second now. Now, I know you discussed this and then I'm looking at the time. Holy crap. Okay. This is a case of a sphere surrounding a point charge. But what we're saying is, in the case of a sphere surrounding a point charge, the total flux through that sphere does not seem to depend on the size of the sphere, right? The r squareds, the r's, cancel out. That means what we're saying is, whether the sphere is big, remember, we're saying flux is total field strength times total surface area. We're saying here, we got that this was the flux for our sphere of size r. Even if we made the sphere size radius 2r, apparently we're saying if we made that sphere twice as big, we might think, well, we have twice as, we might think, well, wait a minute. If you make the radius of the sphere twice as big, that's going to make the surface area of the sphere 4 times as large. Why 4? Because the surface area of the sphere is 4 pi r squared, right? It's an area, it's two-dimensional. So we might think, wait, wait, let me look at this chat. Hold on, this might be good. Right, okay, great question in the chat. So someone's asking in the chat, hold on, they just want to make sure. Does the flux not depend on size in general or only in this case? Okay, very important question. What I'm saying right now I'm talking about this case. In a minute, I'm going to argue that, and this is a special case. We did start with a special, particularly sort of manageable case. Right now, I'm going to make a claim about that case. But in a minute, I'm going to then say that whatever we're learning about this case actually can be generalized to all cases. I mean, so it's an important question. Right now, I'm just talking about this case. I'm saying this, and by this case, I mean a sphere. I am saying that what this calculation seems to show is that if we double the size of the sphere, if we double the radius of the sphere, we would quadruple the surface area of that sphere, right? 4 pi r squared. So we might think at first blush, well, if flux is field times area, if you make twice as big of an area, twice as big an r, you're going to get 4 times as much area. So wouldn't you think we'd get 4 times as much flux? And again, remember, flux is a product. It's multiplication. It's not division. It's not, right? So flux is field times area. So if we make the area bigger, substantially bigger, you'd think we'd make the flux result substantially bigger. But the area of the sphere is directly proportional to r squared. If you double the r, you quadruple the surface area of the sphere. If you triple the r, you multiply the surface area of the sphere by 9, right? It's a function of r squared. But here's the thing. The field is an inverse function of r squared, right? That's like literally why they canceled here. It's not a coincidence. The fact that the r squareds canceled is because surface area of a sphere goes up proportionally to r squared, and field strength goes down proportionally as a function of r squared. Like if we go out to a sphere that's 4 times as big, or 2 times the radius, then the field strength everywhere at that sphere will be 4 times as weak. So what we're saying is, for a sphere, you can make the sphere as bigger and bigger and bigger, but you're just going to make the field strength smaller and smaller and smaller by the exact same amount. How do you see that in the picture? Remember from yesterday, the whole idea of field lines. If you look at these field lines, remember the magnitude of the field at any point is how dense the field lines are, how many number per unit area they are. So as you get to bigger and bigger spheres, the lines are getting more and more spread out. If you did this all to scale, what we're saying is it's by exactly the same amount. It's a function of r squared. So for a sphere, The flux is the same, whether a sphere is this big or this big or this big. Sidebar on, okay. First thing I want you to notice about that, why we're doing this example, first thing I want you to notice about, now again, I understand you discovered this all day already in the lab today. Hopefully, I don't know if I'm making it more clear or less clear or what, but I am saying all. Remember, oh, good. Thank you. Actually, that's very helpful. Good, thank you. Because I'm a little worried that I'm being redundant. So good. And if anybody does think I'm being redundant, or like, if you want, you could tell me that too in the. But okay, good. But I appreciate it.
Wait, I'm sorry. So
Yeah.
just to reiterate what you just said the field strength is inversely proportional to the size of the radius.
Yeah, right. Like field for a point charge. Is like an inverse R squared law.
Oh yeah. Oh yeah. Okay. All right.
Okay.
All right. I get it now. Thanks.
Okay, cool.
When you wrote that, it clicked. Thanks.
Okay, good. No, and that's good. I'm glad. And this is, again, for everybody, even though I'm sending mixed signals, this piece is totally worth dwelling on. This is like the big, I mean, it's the same thing. What I'm trying to say right now, and eventually, we want to, I'm saying, I'm almost triangulating here. Like I'm saying two things. And once you see that they both go in both directions, something might click, like Chris just said it did. I'm saying like, and I'm still talking about a sphere. Someone in direct chat, I will go to bigger examples in a second, but right now I'm talking about a sphere. I'm saying, if you think about a sphere surrounding a point charge, if you ask what's the total amount of fields going through the whole surface area of that sphere, if you just ask the question, like if you're asking yourself to add up all the field strength throughout that whole region of space, because that's in effect what we're asking. We're asking like, what's the accumulated effect of field throughout this particular slice of space? We get an answer, and the answer is Q over epsilon naught. Epsilon naught is just a constant, right? What we're saying, and you now see the reason we started writing K in this funky way of 1 over 4 pi epsilon naught is to get the 4 pi's to cancel and make everything look simpler. Because they invented that idea after they discovered this. But what we're saying is the total amount of field effect on the total surface area of some sphere surrounding a point charge. That's a capital M. I'm sorry, this is a capital. And I will explain that in a second. Okay, cool. What I'm saying is the total effect of field, the total number of field lines busting through the surface area of some globe, some sphere surrounding a point charge in the lab or in the universe, the total amount of field busting through the surface area of a sphere appears not to depend on how big the sphere is. You can make the sphere bigger and bigger, and therefore you would make the amount of area you're adding up bigger and bigger. But every time you make the sphere bigger, you make the field strength at any point on that sphere smaller by the same amount. The sphere, the area of the surface area of a sphere is directly proportional to R squared. The field strength slamming into any point on that surface area is inversely proportional to R squared. So the R squareds cancel. And what we're saying mathematically is no matter how big a sphere you make, the bigger the sphere, the weaker the field per unit on that sphere. So no matter how big a sphere you make, the total amount of flux you get through that sphere is only dependent on how much charge was inside that sphere, the Q, divided by some constant that is a universal constant, never changes, right? It's saying it doesn't matter what you do to the size of the sphere. All that matters is what's inside the sphere. That's what this is saying right now for a sphere. Now, that's already a big deal. It's kind of like why we start with the sphere, because the sphere has this seemingly special property. But before I even go on and generalize it further, and I know I still haven't addressed your debate, believe me, I'm aware that the debate you had, I still haven't even gotten to. Again, hopefully this is worth it to you. But here's, when we say that this is happening in a sphere, we're accidentally also, we're realizing it's not a coincidence. Circle back to day one when we introduced fundamental forces, forces that act at a distance through empty space, the kind of forces that mysteriously just seem to happen by existence, like the fact that one bit of mass can affect another bit of mass through empty space, right? And that's what that second equation is, like the gravitational field due to some source mass obeys an inverse R squared law. Just like the electrostatic field, according to a point charge, obeys an inverse R squared law. And it is going to turn out, when I ever get to it in the last like 5 minutes, that the magnetic field, magnetic action at a distance, also obeys this inverse R squared law. Now, so any law, any force that seems to just happen without touching, any interaction that seems to just arise by virtue of stuff existing in space. I'm being literal, like the electrostatic force, the gravitational force, what will finally be the magnetic force, these fundamental interactions, these interactions that seem to just occur without any touching, without any activity, without any trying. The minute you put a proton in space, it starts pushing and pulling on all other protons and electrons everywhere, right? All of these, first of all, we associate fields with them. We say, well, if that's happening, somehow the information must be sitting in space. The information of proton 1 must be sitting everywhere in space, so that when proton 2 comes along, it somehow feels that information and responds accordingly, right? Like, we always associate fields with these fundamental forces, and these fundamental forces always seem to have this, at first, bizarre math. It is bizarre. At first, it's weird that each one of these has an R squared in the denominator. Like, what is that? That's like out of nowhere. It's annoyingly complicated. It's not directly proportional. It's inversely proportional to the square or something, right? So when you first see any one of these forces, if you're anything like me, you're like, oh, what is that? And then when you realize that it keeps coming up again, and eventually you have to ask, or any physicist asks, why is it that every time we see a fundamental force, they always have this inverse R squared feature? Well, here's the reason. Because a fundamental force or fundamental field is spreading out through space. Space is the same in all directions. So the effect of the force, the field information, spreads out everywhere the same in all directions of space in the manner of a sphere. Like, what we're saying is the field from a dot spreads out spherically through space, and anywhere, any sphere that we pick, like, the field gets weaker and weaker as it goes out, just like if water were to be sprayed out from a spigot, in jets, the intensity of the water would get thinner and thinner as you got farther and farther away from water. But if you were at a given distance, it would be the same thinness of water, or whatever you want to call weakness of water, everywhere at that distance, right? Because there's no reason that the field to the left should be doing anything different from the field line to the right. They're just spreading out through even, homogeneous, symmetric space. So field lines spread out in magnitude in the manner of a sphere. In other words, the fact that the R squareds cancel is because the field equation is an inverse R squared equation. Why is it an inverse R squared equation? Because it's spreading out like a sphere. And this is why we focus right away on what's the effect of this field on a sphere, because we can right away see, oh, it's the same no matter what size sphere you get. If you didn't catch all that, don't worry about all what right now. I'm just saying, right now I'm saying, because I am certainly saying, like one person in the chat asked, I'm certainly saying that anything we're saying right now about electricity would also be true of gravitation and ultimately of magnetism. If it's an inverse R squared function, it's going to have the same effect anywhere in the surface of a sphere, no matter what the size of the sphere is, right? That is what I'm saying right now. But then I'm going to say more. Okay, let me, but this thing's happening in the chat. So I'll pause for a second. Hold on. Oh, sorry. Oh, did I? Oh, I did answer. Okay, okay. I think I answered. Okay, okay. So now, so back to, so someone asked in the chat, very wisely asked, hold on, are we saying this is true in this case or in all cases? So right now, I'm making a claim about this case, the case of a sphere. I'm saying the size of a sphere is directly proportional to r squared. These fields get weaker and weaker as a function of r squared. It's not a coincidence. It's why they do. The r squareds cancel. And so the total impact of field on a whole surface area of a sphere is the result we just got. Sorry. So for a sphere, a radius r, well, let's be really clear. Centered on a point source Q, we're saying this we're saying that the total flux, the total impact of field throughout that surrounding area, that enclosing area, is independent of size of sphere. But now, someone in the chat asked, okay, well, what if it's not a sphere? And then we're going to get closer to the debate you had in the board meeting. What if it's not a sphere? Well, to cut to the chase, I mean, and that's a very important question. I mean, obviously, a sphere is special because what is a sphere? A sphere. Okay, what a sphere is a locus of points equidistant from a given point, right? I mean, in English, what a sphere is a shape where the r, the radius, the distance from the edge of the shape to the center of the shape, where the r is the same everywhere throughout that shape, right? A perfect sphere means r is perfectly constant. It never changes, right? So if we change from a sphere to some other shape, imagine that the sphere is made of clay. And we start deforming the clay and like pinching it and pulling pieces out and maybe warping the clay until we make like either like a square, I mean like a cube or an oval or like a football or whatever, or maybe some completely ridiculous thing like an elephant. Well, we'll get to that in a minute. But let's first say that we change the sphere into some other shape that might be symmetric, might be nice and regular, but might not be a sphere, like a cube, right? Well, if you really think about it, what does that mean? That means we're now making a shape. I mean, it's a good question. Does this whole result still hold up? Like we only just proved it for a sphere. But the thing is, if you change the sphere to a cube, if you take that clay and you bend it and warp it into a cube, what have you done? You've now said, okay, somewhere over here, the R is one thing, but then over here, the R is another thing. Like the distance from the center to the middle of a face of a cube would be like a very short r. But then if you went from the center, like where the point charge is, all the way to a corner or a vertex of the cube, then that might be a much longer r, right? Like that's why it's not a good sphere anymore. Like any other shape is a supremely imperfect sphere. Any other shape is a shape that has lots and lots of different r's from the center. So that's not a sphere. But we just proved that r doesn't matter. We just showed that the r's cancel out. So what? I mean, I'm sounding sarcastic. I don't mean to say it's a stupid question, but it's actually kind of wild if you think about the answers. If we change from the sphere to some other shape, at least some other regular shape, all we're doing is relaxing the assumption that r is constant. But apparently r doesn't matter. So who cares if it varies? And I'll make a different, I'll try to demonstrate this result in a different way in a moment. But right now, what I'm saying to the direct chat and to anybody else is if we change. So right now we've said that this result, that the flux through the surface only depends on the charge inside the surface. First, we just showed as long as that surface is a sphere, the size of the sphere doesn't matter. Now I'm claiming if we change the shape from sphere to some other regular shape, some other symmetric shape, let's say,
Would a disk be considered symmetric?
it would certainly have symmetry. Yeah, it wouldn't be symmetric in all dimensions, but it would have two-dimensional symmetry. Yes. And by the way, and don't even, but so yes, but I'm going to get to the asymmetry thing in a second. I'm just trying to sort of go bit by bit because I know it was your
No.
debate. But
No, I mean, what if the E field was using a disk? What if the E field was emitted at like an angle? Would it still be the same case that it wouldn't? It would still be the same even if the shape changed from a sphere to a disk.
so what I'm claiming again, very good question. What I'm claiming right now is that even we change to a disk, it seems to me the total flux will not be affected. The total, okay, cool. The total flux will, cool. All right, I'm just seeing something in the chat. I'm claiming that even if we change the shape surrounding that point charge, the total flux through that shape, the total answer to the integral would still be the same because supposedly,
Here are some results.
oh my God, wait, okay, sorry, my board thinks I'm asking Siri to teach me physics. Sorry. I'm claiming that if we really believe what we just did, that our result doesn't depend on R, then even if we start messing with R and making it vary from point to point on our surface, our total flux result should be unaffected. Now, that's what I'm claiming. And I'll even go, and I'm going to give another explanation for that in a second, but I know where you're going. I mean, I think you still have a reasonable concern. There's something that seems bad about a disk. There's something in your gut that's saying, but a disk can't be as good as a sphere somehow. And there is a way in which it's not. And I do want to address that. But in a minute, like what I'm just saying right now, in fact, I'm going to give my other explanation right now. I'll even go, okay, so bear with me for a second. I'm going to go so far as to say, even if, and this is where the debate comes in, even if the Gaussian surface, the surrounding surface that we've picked, the closed surface, even if the Gaussian surface is hideously, that's not a scientific term, but asymmetric, if it's like ridiculous, if it's like a three-dimensional paramecium or something, like a blob, right? The total flux should still be the same as what we just found. And I'll tell you why, but it doesn't mean your concern's not justified. But if we're following this logic, and this is the very obscure thing that went really fast at the end of yesterday, but I want everybody to see this now because I don't know if it was said in lab today. What I'm saying is, so right now I am claiming, and you can write down, I'm claiming that if you really believe the result we just got for the simple case of a sphere, I'm saying we can now mess the crap out of that sphere to the point where it's a blob, and our flux result should still be the same. According to our logic says R doesn't matter. So it seems to me we can play any games we want with R and it shouldn't matter. But let me give you another. It doesn't mean we're done. It doesn't mean your whole debate is resolved, because those of you who are concerned about asymmetric shapes today, you're right to be concerned, and I still want to address that. But just bear with me for a second. What I want to say is, and again, I couldn't be prouder that you had that debate, but what I want to say right now is recall, what's really, I want you to recall something from yesterday that went very fast. One thing, even those of you who are still following me, sort of, what might be bothering some of you is, all right, you might be thinking something like, all right, I'm sort of bothering this, and we sort of already did it today, so I sort of get what he's saying, but you might not feel like you totally get it, because there still might be a part of your brain going, but why the heck do I care? Like, where did this whole flux concern come from in the first place? Like, why? Like, I was just learning about field like 2 days ago, and then suddenly it became flux. Like, what is going on? One thing I want to tell you is there's a couple of reasons we suddenly get into flux really fast the minute we understand field lines. The one reason we get into flux is we're trying to show you right now. Flux is something that remains constant and reliable even under really weird changing conditions. Field does not. It's just like how you learned about force for a while in mechanics, but then eventually we started applying forces to paths and creating this idea called work and energy, because it turned out that under lots of conditions where the forces were changing continuously as a function of space, like even when you had like pendulums where the force kept changing all the time, the magnitude of the force and the direction of the force, we could say things like, aha, even though the force is changing, this whole integral called the work energy integral is remaining constant. And as long as we know something about work and conservative work and blah, 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 we could say there's something called energy that's remaining constant for a system. So we started using energy as a way of looking at systems even when the force was changing, like masses on springs. Similarly here, one of the reasons we're diving into flux is that there's fields, as you saw from those field line pictures, fields change wildly all over space, even in really simple situations. But flux is something that we can grab onto as a reliable constant, as this whole example is trying to show. And one of the reasons we can grab onto flux, which is not the same thing as field, right? It's field times area. But bizarrely, even though field will change and area will change, somehow the product of the two will stay the same under lots of situations because, recall, flux is defined to be field strength times area, right? In simple terms, forget the integral, forget the dot product and all that. Flux is field strength times area, right? And field strength, remember, is number of field lines per area on the page. So if you multiply that by area, all you're talking about is counting the field lines. For all of this crazy math we're doing now, and I'm not trying to disappoint you or trick you, but I'm trying to say the reason Faraday started focusing all of our attentions on flux is because flux means strength times area. Strength is represented by number of field lines per area. So if you multiply number of field lines per area times area, you're just talking about the number of lines. So look back to your original example that you're talking about in the lab. And this will, again, hopefully address some of the debate you're having. If here's our example, hello. After all that math or before all that math, here's our example, is a dot in the middle of the lab with a bunch of field lines coming out of it. If flux means number of field lines that you count penetrating some area, if that's what flux means, it's you pick an area and you count the number of field lines busting out of that area, right? That is what flux means. It means count the lines once you have a scaling factor and all that. So look, if I drew a sphere right here, there's 8 lines coming out of that sphere. If I drew a much bigger sphere way out there, I think you can all see it would still be 8 lines coming out of that sphere. And actually now, if you're really seeing that flux just actually means count the lines, which is what it does mean, then if I made a crazy shape right out here, like an elephant, a cow, a Gaussian cow, whatever, some irregular Picasso drawing sculpture out here, the number of lines that would bust out of that crazy figure would still have to be 8. It would have to be 8 lines. Why? Because field lines never start or stop spontaneously in space. They only start at positives or come in from infinity. So we got one positive charge here. 8 lines are coming out of it. What our result is saying is that the flux through our sphere, the number of lines coming through our sphere, is totally determined by how much charge was inside that sphere, right? For the sphere, that's what it's saying. But now what I'm saying to all of you is this is why field lines are so important. If you can get your mind, and it doesn't happen overnight, but if you can really see why fields are serious, real. Field is information sitting in space. It has to be there. Otherwise, protons couldn't pull on electrons through empty space. The way we picture the information sitting in space is with these lines. These lines follow rules. They represent reality precisely, the same way graphs or vectors or anything else, or numerals for that matter, do. So if you start taking the rules and of the lines seriously, then what we just said, that if 8 lines are coming out of a proton in the lab, if you surround that proton with a sphere, of course, 8 lines are going to bust through the sphere. And if you change that sphere to a much bigger thing that's actually an elephant, then 8 lines are still going to bust through that elephant, because the lines are only there. The only lines that will come through the elephant at all are lines that got created by that proton inside the elephant. And then you might even say, but wait a minute, what if there's some proton outside the elephant? Well, sure. If there's a proton outside the elephant, it'll create a line that will go into the elephant, but eventually it's going to come out of the elephant, because field lines start at positives and then go on forever. I mean, electric field lines do, right? So actually I'm saying very firmly now, if you take the math and the lines seriously, I am literally saying that even if the Gaussian surface is hideously asymmetric, the total flux should still be the same. Flux just equals number of lines through an area. Lines start at positive. So I'm saying, and Gauss is saying, and I'll to finish this now, or to finish this point, everything I just said about that dot in the middle of your sphere would be true of any dot in the middle of your sphere, or any two, like for every dot that you draw a sphere around, it will create this situation. So if you put 2 dots like really far away and they each have a sphere around them, then each sphere will obey this law. If you put 2 dots really close together, and they create one of those field line diagrams that we saw on Google Images the other day, like so say you put 2 protons right next to each other. So they each create 8 field lines. Now the field lines will start bending and making the whole more complicated pattern, but there still has to be 8 field lines from each of those dots. A total of 16 lines somehow will come out of whatever shape you surround the 2 dots in. So what I am saying, and bear with me again for a second, I am saying, and of course you debated about it, because it's actually bizarrely surprising. It's a wild what we're saying at the end of the day. If we surround source charge with any closed, or what we now from now will call Gaussian surface, with any closed surface, the net flux out of the surface will depend only on magnitude of charge enclosed by the surface. I'll go back to, I'm just going to keep writing for a second, but if you need me, well, I'll pause for a second. So it says, at the end of the day, if we surround source charge with any closed or Gaussian surface, the net flux, the net E flux, out of that surface will depend only on magnitude of charge enclosed by the surface. Remember again, a closed surface necessarily is the boundary to an enclosed, a unique volume. So we're saying you make any container in the world, or you imagine any container in the world, a closed surface is a container, right? You imagine a tennis ball can or a sphere or an elephant or whatever, any closed surface, any container in the world, the total amount of flux that will be coming out of that surface will be determined fully by the total magnitude, the total amount of charge found within, found enclosed, found in the volume bounded by that enclosure. It will be fully determined by that, the net flux outside, in other words, will be independent of one, size of Gaussian shape, two, shape, size of Gaussian surface, I should say, the enclosing surface, the closed surface, shape and and symmetry of Gaussian surface, shape of charge enclosed. Like, it won't matter how the charge inside, this is another question that someone was asking me in the chat and may have been part of your debate. I don't care how irregular that shape is, this result will still be the same. And I don't care how irregular the charge inside is distributed, how irregularly the charge inside is distributed. Every point inside will create this effect, will create field lines that have to go on forever and eventually hit the surface. And if there's two charges, they're each going to create field lines. Their field lines will make each other bend, like they'll make some funny pattern, but the field lines cannot disappear spontaneously in space. So the shape of charge enclosed won't matter. And also, finally, charge outside the surface won't matter. So these four things all don't affect the flux result. That's why this result is really powerful. It's why we care about flux. Now, again, I'm going to say, and I'm going to go, I still have a lot to say, sadly, or goodly, but and there's still more about your debate to address. But I am saying right now, the reason we care about flux is flux just means count the field lines. And so this whole result that I just wrote down is all summarized. This is all then we're saying for any closed surface, the net flux, the total amount of flux flowing out of that surface will always be fully determined by the charge enclosed by that surface divided by a fundamental constant. Q enclosed means the magnitude. It doesn't even notice, it doesn't have a vector symbol over it. Like the left side is a dot product. You dot two vectors together, you get a scalar result. The right side is a scalar. We're literally just saying, you go to any container anywhere, imagine any container anywhere in space, you want to know the total amount of flux emanating out of that container. It will be fully determined by whatever charge you contained in the container, whatever amount of charge. I don't care. And it won't be at all affected by the size of your container, the shape of your container, the regularity or symmetry of your container. It won't be affected by how the charge is distributed on the inside, and it won't be affected by any charge on the outside. Flux is that reliable and that constant, and therefore that useful. And again, if you want a mental picture of what the heck I'm talking about when I say so mathematically, I'm saying, wait, so this is Gauss's law, right? This is Gauss's law. Again, notice we went from the original, the definition of flux was a triple equal sign, and it just said flux is, the sum of field times area. But now we're saying, as long as you calculate flux through a closed area, as long as you make that restriction, then double equal sign flux always ends up being fully determined by what's within the enclosure. So again, it's kind of like saying we define work to be force acting through a displacement, but then it turns out that work always is transfer of energy, and that's why we care about it, right? Similar kind of thing going on here. Sorry, I will take a breath someday, but hold on. So this is Gauss's law. Oh, so this turns out to be really useful, because then we're going to use this result. And I have to do at least one example now before class is over today. I want to show you, we haven't used it yet, right? We're just showing that it's true from the example you did in the board meeting. We haven't used it. We're showing it. Oh, yeah, that's a fair, all right, fair question. Hang on one second. I don't know if that was to everyone or to, that's the, okay, yeah. yeah, sure. It might be mini, but yes, I know this is a lot. Let me just summarize this and then we'll pause first. I mean, someone in the chat is very reasonably asking for a mini mental break, which I think is totally fair. Just bear with me first. So, and you can thank him or her later. But give me a second and then yes, but it will have to be mini because there's still a lot to do. But here's what I'm saying right now. In sum, I'm saying that charges are like spigots or sprinklers, and field lines are like jets of water. If you want to just back, here comes a little pre-mental break. Just back off all this math for a second. I'm actually saying, think about this. If you ever put a sprinkler, right, like one of those suburban things like Long Island that like spreads water everywhere, right? Imagine you have a sprinkler that's like shooting jets of water everywhere. If you were to surround the sprinkler with a tarp, like with a tent, or put the sprinkler inside a tent, if you think about it, it doesn't matter what the shape of the tent is, and it doesn't matter what the size of the tent is, and it doesn't matter what's going on outside the tent. If there's a certain number of drops of water coming out of that sprinkler, like in an hour, then an hour later, you're going to have exactly that much water accumulated on the inner surface of the tent. Right, the total amount of water accumulated on a surface, or if the tent like was semi-permeable membrane, if it was like screens, and you're counting how much water like busted out through the tent, the amount of water that would seep through the tent in an hour would literally be exactly only whatever number of drops of water ever came out of the sprinkler in the first place, because water is neither created nor destroyed, right? Like none of this would even be surprising or interesting at all if we were talking about water. All we're saying is the total amount of water accumulated on the inside of some surface is fully determined by how much water was sent out from somewhere within that surface. So we're literally, if you can follow what I just said, that's what I'm saying about electrical field lines. And if you're wondering, well, why the heck didn't I just say that at the beginning? Well, in a weird way, yesterday I did. But really, the thing is, what we're saying here is that's how real field lines are. Field lines act like water. Field lines are not thingy, but they act like thingy things. They are information, but the only information that gets accumulated through any surface or any region of space is only and fully the information that came out from the information's source somewhere within that space. In this case, the sprinkler is like a charge. Charge sends out electrical field lines, like sprinklers send out jets of water. And the Gauss's result is to say, oh, wait, so from here on in, let's just focus on the total amount of field lines that accumulate on some surface, because it's going to be really reliable. Because what we're really saying here is if 8 freaking lines come out of some proton, then we'll know in advance, no matter what surface we ever pick to surround that proton, there's going to be 8 lines that bust through that surface. A flux, in the end of the day, just means number of lines, which is a representation. But as long as you pick a scaling factor and you're consistent with it, then the representation precisely maps to reality. So we're saying the number of field lines through any closed surface, number of electric field lines through coming out of any closed surface is fully determined by the charge enclosed within that surface. That's what we're saying right now. It's huge. It's a lot. We'll take a break in a second, but that's Gauss's law. What we have to do after a quick mental break in a second is I have to show you how to use it, why we use, like one example. I'm just going to do one quick example right now of how we use it to make our life better. And when I do that example, you'll see even more why the debate you guys were having about symmetry versus asymmetry was a very robust, honorable debate, no matter what you think I've said so far about it. Okay, but yes, this is a lot. We still do have a lot though. So let's take like a 5-minute break, like to clear your head, balance your fluids, whatever. So I'm going to I think it's 6:06 right now. I'm going to start at 6:11. Okay. I have to be a little bit strict just because we're at that, but yes, take a break. Okay, cool. Oh, okay. Wait. Oh, okay. And I'm still here. But you guys go take a 5-minute break, but take it fast. Wait, actually, I'll turn off my video just so you know. Okay. But I'm still here. Yeah, wait, hold on. Oh, all right. I'm gonna start again. I know, and obviously some people might still be coming back. Hold on. All right. No, we still have more to do. Of course, you're all being, I do know this is a lot. Um, just raise your electronic hand if you're mentally still with me, sort of. Thank you. And by that, I just mean if you're in the, yeah, okay, cool. I don't, and you can't, I mean, this is where physics becomes physics. Okay. This is real physics now for what it's worth. And the part of your goal, again, we're trying to get to the end of a story. I think this is all worth it because I think you're going to see a punchline at the end of tomorrow that makes this all worth it, at least to me. But this is where physics becomes like the point of class is to see what the material is. And there's no way, I mean, it only sinks in after debate and practice and blah, blah, blah. Anyway, on your own time. I mean, anyway, but so don't think if it's not all driving right now for you that something's wrong with you. No way. Like that's not the case. But okay, but I still have to go on. So but thank you for raising your hands. And you could keep asking the questions. What I have to do now is I have to do at least one. Oh, and again, remember, no matter what, I hope you see now too with the whatever's on the final exam, which you'll basically find out you'll find out when you walk into the room tomorrow, I guess, or maybe late tonight. I have to think. I don't know. Maybe I'll whatever the practice thing that you're going to do tomorrow that maybe I'll post later tonight. I can't decide, but you know that I'm not going to ask you. It's not like you have to, I'm teaching these examples and then I'm going to ask you all these different examples on the final. It's not that type of material. The point is to understand these classic cases and understand their implications. And that's hard enough. It's not, anyway, you get my point. So what I have to do now is I have to do at least one example to show you how we make use of this law. Like, I mean, what this law is saying in a way is that field lines exist. They act like water. I mean, in a way, that's what it's saying. Or another way to put it is like, if you could, whatever you believe about water, you can apply to field lines. But then that means flux becomes a very useful way for us to, sorry. Um, um, hold on one second. Hmm. One second, I'm sorry. Okay, okay, so we have to do an example. We're going to do an example now of how we use this result. So here we go. Okay, so I'll read that out loud. I'm saying, okay, so here's our one application or example. We're going to consider, I'm going to draw this in a minute, obviously, but we're going to consider a solid sphere of negative charge, negative source charge throughout the whole sphere. Radius r. So this is now our situation. Our source for the first time now is a ball, right? We're now getting finally to like reality, not just a dot, but so many dots that they make a solid shape, a ball. And there's negative source charge throughout the whole thing now, okay? And the ball, so it's like this. The ball has radius r and it's negative q distributed like plum pudding, right? Like everywhere, solidly, but uniformly. So there's negative charge. So this is a new situation. This is like finally the point of why we're doing all this, because we already have a law to deal with one point at a time. But now how can we deal with like a continuous configuration of charge, like a ball of charge, like a Van de Graaff generator is what this would be like, right? Okay. And so it's definitely a step up in our given situation, but it's not crazy. We're assuming r in negative q, and we're also going to assume that like we're going to use lowercase rho, the Greek letter lowercase rho. It looks sort of like the Greek letter rho, to stand for just trying to think how complicated. Okay. Okay, this thing that I just wrote that looks very complicated, in English, what I'm saying is Okay. There's another new piece of notation. Oh, I'm sorry, Evelyn, is that a question or is that just a hand from before? I'm sorry. Wait. Oh, okay. And is it R negative U? Yeah. Okay. So the givens are that the radius of this ball is capital R. Yes. I'm answering in direct chat here. And another given is that negative Q is the total amount, like the total amount of source charge. It's now not just a point, it's a ball of charge, but I'm intentionally making it negative now to up the ante. And then I'm saying let rho, this Greek letter, you don't have to get too bogged down in the Greek letter, but I'm saying the density, the three-dimensional density of charge, the amount of charge per unit volume. So I'm using that V with serifs over it to mean like volume. You can use whatever symbol you want. But I'm saying charge per unit volume, just like, in chemistry, mass per volume is density. Well, we're talking about charge density now. So charge per unit volume is like charge density. And I'm saying, what I'm trying to say is rho equals rho naught, meaning the density is a constant. For any cubic centimeter of space that you pick in the ball over here, it has a certain amount of charge in it. Well, if you pick a cubic centimeter over there, it'll have the same amount of charge in it. And if you pick 2 cubic centimeters over here, it'll have twice as much charge in it. It's not supposed to be a trick, even though it's a lot of new notation. It's meant to actually simplify the situation. I'm just saying the charge is uniformly distributed throughout the sphere. That's what I'm trying to say, okay? And the question, our question is going to be, at some independent variable displacement lowercase r, so imagine a vector lowercase r from the center of this sphere, right, at some lowercase distance r at the center of the sphere, I want to know what is the field, what is the electrostatic field function at that displacement lowercase r. That's the question. Okay, I'm going to write it. So this is the setup. This is a new kind of setup now. Now we have 25 minutes, right? I mean, I imagine this is all I'll do today. It's fine, but we have to at least do this. Let me be very clear. We have a new setup. It's a continuous charge distribution. It's like it's a bunch of charge now, and it's so much charge that it's continuously collected, right? So we don't have a formula for this. We don't have an equation for this. We have an equation that says what 1 point of charge produces in the universe. We've got this ball of charge, of negative charge here, and I want to know what the field is somewhere in the interior, somewhere at some arbitrary radial distance, somewhere in the interior of the sphere. I want to know what the electrostatic field is, magnitude and direction. Now, that's a very new question. Remember, I originally said the whole point of electrostatics always is I tell you some charge over here. I want to know the field over there. That's what I'm doing here. Only I'm asking about the field sort of right within this whole forest of charge. Well, the question is going to be, I'm going to again write it on. So those are the givens. The question is, what is electrostatic field as a function of R? And at least for this case, we're assuming that R is smaller than capital R. That is, we're assuming that we're looking at some point in the interior of this globe. We could also get an answer for the exterior, and we would follow the same procedure to get it. But I'll tell you right now, it'd be a different answer. So I'm just being specific here. We're gonna find the field. Note. Okay, two quick things. This is a standard classic question in electrodynamics. Like if you took a whole course just in electrodynamics or whatever, as meant, if we were physics majors and we were taking a whole course in electrodynamics, like would be one problem after another of this nature, where you give a situation and then you're asked to find the field as a function of R vector. Note two things. The question here is what's the field? The question is field. Now I know we've just been talking about flux for a million hours. Don't worry, you'll see why. But the thing we ultimately care about in physics, is field. Field at a point is what will push or pull protons or electrons at that point. So we're trying to find field here. And second of all, we want to find it as a function. We're not going to get a number when we do this. We're going to get it as a function. We're going to see how the field at a given location within this whole globe depends on how far away we are from the center of that globe. Okay, so that's our goal. We're about to be interrupted again. Maybe not. Okay, we want to find field. We want to find it as a general function. And field is always the ultimate goal in electrodynamics. Now, you might ask, well, why the heck did we just talk about flux for 400,000 hours? Because flux is the way that we get field. And I want to alert you to that. I mean, in the next 20 minutes, as we do this, what you're going to see is we're going to use Gauss's law. Well, I'm going to write that. Well, I'm going to write this down, but we're going to use the Gauss's law result in order to get field. But it's very important to sort of know that while we do this. I know many of your brains are already on overload. I respect that. And thank you for hanging in. But to keep the flux is a application of field. They're two different concepts. Flux is counting the number of field lines, but field is the lines themselves. We're going to use the result that just like you might use energy conservation in order to figure out how fast a mass is going on a spring. Like you care about how fast the mass is going at a moment, but you use energy conservation to get there. We're going to use the Gaussian result about flux in order to get the field. And that's what the purpose of the Gauss's law is. So here we go. In order to solve for field given continuous charge distributions, we use Gauss's law and the Gaussian procedure. So here we go. Now, you know, I'm a big fan of the 5-step problem solving method, all that. There's to do a Gauss's law problem, you could still always do the 5-step method, but there's actually like 5 specific mini steps that completely apply to Gauss's law. So we'll call them something else. We won't call them steps, but here they are. The Gaussian method. So what that just said, we're going to use Gauss's law and the Gaussian method for solving these problems, for solving for field. So I'll call it, here we go. Instead of calling, this is all within the 5-step method, but I'll call it Planck 1. You know, that's like a mini step. Planck 1. We draw the field lines, the field line diagram for the situation. Okay. So we're going to follow all the rules as we always do for field lines. Here we have the situation, right? I'm going to draw the field lines. We got a bunch of charges everywhere that are all producing field lines. But remember, field lines are the most symmetric, smooth assortment of lines that you could draw given a certain scaling factor. Let's do our normal scaling factor of like 8 lines per every Q. This thing is spherically symmetric. I think that the lines are going to be spherically symmetric, right? The only thing is that this is all negative Q, so I think all the lines are going to point in. And I don't think the lines are going to start at the edge because there's charge everywhere. So there's going to be field lines everywhere. In other words, I'm going fast right now, but this is what I think the field line picture would look like. It's the simple, it's if you were forced right now out of nowhere to come up with a field line picture yourself and you looked back at the rules from yesterday, honestly, this is what you would come up with, but then you would think it was too easy and you'd second guess yourself. But the whole point of the field line picture is it's supposed to be as symmetric. It's only as asymmetric or as complicated as the thing that caused it. A ball caused these lines. So these lines are spherically symmetric. And there they are. So I made 8 lines, but they're all going in, right? Because this is negative charge. And they come out from infinity and they just go into the center. That's my field line picture. Okay, done. You can think about that. So Planck 1 was draw the field line diagram. Remember, I'm trying to solve for field here. Planck 2, and I'm saying Planck again because this is a procedure that always works and you can memorize, you know, it's almost a relief because it's just a procedure. So Planck number 2, okay, I'm going to choose and draw a Gaussian surface at R. What do I mean by that? Okay, I'm going to go back to the picture. So what I do now, here's the point of everything you did in the lab today. Here's the point. What you concluded, or what I concluded with you, is that flux is something that is true no matter what shape. Any closed surface, the flux through a closed surface is fully determined by whatever's inside that surface, nothing else. So I could put I ultimately want to know the field. I ultimately want to know the field, right here at that displacement R. Now, what is special about R? Nothing, but R just is a vector pointing to a certain spot. It just represents where I'm looking, right? And if I get the answer for that particular R, the point is that'll be the answer for any R. So I'm trying to figure out what the field is at that displacement R. I could put a cow, there that contains that point R. I could put a cube. I could put a sphere, and whatever shape I put, symmetric or asymmetric, any shape I put there, Gauss's law would apply to it. The total amount of flux through any shape I imagine to be at distance R will obey Gauss's law. So the power of Gauss's law is I can choose any shape I want. But therefore, and this is just like this is such physics. The point is, since the law would be true for any shape, I will pick a shape that will make the law worthwhile to use. I will pick a shape for which the law will actually make my math very easy and convenient, kind of like the sphere that we picked at the beginning of this whole discussion. What do I mean by that? I want to choose a surface. I could choose any surface, just like with Galileo. Laws of physics are the same in all inertial reference frames, but therefore we choose inertial reference frames that give us convenient calculations. It's a way of using physics to reduce math. They're not the same thing, right? So I'm going to pick a surface that makes my math easy. What does that mean? Well, in simple terms, it means I'm going to pick a surface that mimics or appropriates the symmetry of the situation itself. This is where a lot of you in lab today were probably more right than you think when you were insisting on some kind of symmetry. The law will work even for an asymmetric shape, but the law won't be useful, you're about to see, unless I pick a symmetric shape. And so that's why everybody had a point today, as far as I know. What I specifically mean is when I say choose and draw a shape, a Gaussian shape, I could choose any, but what I want to do is choose and draw a surface for which E is constant in magnitude and direction, right? The E vector, I want to be constant in magnitude and direction with respect to ds. In other words, I want to choose a shape so that when I apply the flux integral of Gauss's law, this is the whole point of Gauss's law. That flux integral, which can look very intimidating, is always whatever it is, no matter what shape you pick. So if we pick a shape for which the E doesn't change with respect to ds, for which the E is a constant, like it was before, then the E will come out of the integral, and then we don't have to do the integral. And the whole point of this integral, believe it or not, and the whole point of this whole method is you got to understand enough about integrals to know how to set up the appropriate integral so that, in fact, you don't have to solve it. That is the point of all this. So we're going to pick a shape for which the E field vectors are hit with the same density and the same angle everywhere on the surface. Well, in this case, that will mean, in other words, it means mimic the symmetry. So it means I'm going to draw a Gaussian surface. I'm going to draw a Gaussian sphere, which you probably saw coming right at that brown dot at R. I'm drawing a Gaussian sphere of radius R. Now, this is getting confusing already, I'm sure, to some of you. Remember, the outer sphere is like real. The outer sphere of radius capital R is the actual ball of charge sitting in the lab that we're analyzing. Now, but we're trying to analyze what's going on in the interior of that ball. So in our minds, we draw a Gaussian sphere at the interior point that we're interested in. If you're thinking to yourself, so wait, is it always spheres? Is it always spheres? Well, honestly, no. Like if we were looking at a charged line, we would draw a cylinder around it. If we were looking at a charged plate, we would draw a box around it. Like what we're always ultimately doing. So it's not always spheres, but it is always some kind of shape that picks up on the symmetry of the charge shape. So again, those of you in the lab today that were insisting on symmetry, what you were getting at is this law is only useful. It's always true, but the power of it is that it's always true. Therefore, we can pick whatever shape we want. Therefore, we deliberately pick shapes with symmetry because now that I've picked, like mimic the symmetry of the charge distribution, mimic the symmetry of Q. Always, that's what you do. So now Planck 4 of the method, and I know there's 11 minutes stuff, we'll get there. Planck 3, sorry, is we literally, well, technically, verify, Planck 3 technically is verify that E really is constant with respect to the surface. And look, if you look at that picture, I'm not going to flip again. We're saying just the same thing I said 2 hours ago. Any field line that hits the surface of a sphere, well, anywhere you look on the surface of that brown Gaussian interior sphere that I'm imagining, the field lines are always hitting it with the same density, and they're always, i.e. magnitude, and they're always hitting it at the same angle, which is to say perpendicular to the area. So it was a good surface we picked. So check. So now Planck 4, we write down Gauss's law. So here's Gauss's law. We write it down. Gauss's law is this. Now, again, remember, this time now, what we did for hours and hours today is you sort of generated Gauss's law to get some result about the flux. Now I'm using that result. I'm saying flux is always the same. Here's the law. The flux through this closed surface is always the same. I'm using this in order to compute E, right? So I wrote down Gauss's law. Now look, Planck 5, take out E and expand both sides. Meaning, if we pick the right surface, we can take the E out of the integral. We're always going to take E out of the integral, but in order to do it, we have to pick the right surface. The art of this whole thing is we have to physically follow these concepts in order to get out of the math. That's what Gauss was famous for, by the way. He was a genius for working out ways to get out of doing work. Like there's all these kind of stories about him that way, but that's what we're doing. So I'm saying you're always going to take the E out of the integral, but you have to pick the right shape in order to do that. Anyway, so here we go. Because we picked the shape that E is the same throughout all the DS's, we're doing Planck 4, we're going to write, okay, E. And it means the vector symbols went away too, because the cosine of the cosine of the angle was always 1. Okay. So we have this, okay? Okay, so now we're almost done. We're almost done, right? E, just like before, E times integral of ds. Okay, well, integral of ds means total surface area. Total surface area of what? Of the sphere. Of what sphere? The Gaussian sphere. The total surface, so not the original given sphere, the Gaussian sphere at lowercase r. The total surface area of the Gaussian sphere of radius lowercase r is 4 pi r squared. I'm looking at the time, we've got 8 minutes, okay. So the left side is E times 4 pi r squared, right? Now that equals Q enclosed over epsilon naught. We're almost done, but now let's be careful. Q enclosed means the total charge enclosed within the Gaussian sphere. In other words, the total amount of flux coming out of the sphere we're picturing, which is somewhere in the interior of that original ball, because that's where we're trying to find out the field. The total amount of flux busting out of that interior sphere is determined fully by the total amount of charge within it. Now, again, I don't care that it's a whole ball. Like, it doesn't matter how it's distributed. The total amount is what's determining the flux coming out, because it's like the sprinkler water thing. The total charge but that means total charge enclosed within the Gaussian sphere. So what is that? That is not just capital Q. We have 7 minutes left. Capital Q is the total charge everywhere, throughout the whole ball. We're specifically looking at some sort of inner ball of it. We're only enclosing, remember, charge on the outside does not matter. Only charge on the inside of a closed surface affects flux. So Planck 5, the final thing, Planck 5, make sure, like sometimes you have to focus hard on to evaluate Q enclosed. It doesn't always, Q enclosed does not always equal the given Q, and solve. So this, the last thing is, so what is Q enclosed? I don't know, but I know this. I was told at the beginning that there's 6 minutes left. I was told at the beginning that charge per unit volume is a constant, right? The density of this charge is distributed throughout. So I know rho is a constant. So I know that the total charge per the total volume must equal the charge enclosed divided by the volume enclosed, right? The ratios have to be the same. We're almost done. I'll just write that again. So the total charge per the total, volume must equal the charge enclosed divided by the enclosed volume. Well, now we're talking volume now. Volume, right? The left side of Gauss's law is all about closed surface, which is the boundary, to the right side of Gauss's law, which is the enclosed volume. The left side of Gauss's law makes a statement about two-dimensional space, and the right side is talking about three-dimensional space. So what's the volume of a sphere? The volume is 4/3 pi r cubed, capital R, because that's the total volume of the whole thing. And what's the volume of the interior Gaussian sphere? 4/3 pi lowercase r cubed. So the 4/3 cancel, the pi's cancel, and at the end of the day, and I am watching the clock, and we are just about done, I promise. The charge enclosed equals the charge times this ratio, lowercase r cubed over r capital R cubed. That might look really weird to you, but if you really back up and think about it, it actually makes sense. It's basically saying the charge enclosed is some portion of the total charge. What portion? Well, it's the portion corresponding to however far out from the center you're going. You might think it would just be r divided by lowercase r divided by r. Like if you went halfway out, you might think I've enclosed half of the total charge. But if you go out along the radius, the space that you're in is three-dimensional. So if you go out 1/2 of the radius, since the volume of a sphere is proportional to the cube of the radius, because three-dimensional space, if you go out halfway along the sphere, you will enclose 1/8 of the total charge. That's what this is saying. Who cares? Well, now we can just plug this back in and we're done. Plug in. So we're saying what we had was E times, I don't know how this whole thing became brown, but E times 4 pi r squared equals Q times r third over. Right, I just plugged it back in. You'll look back at your notes later and you'll see I just plugged it back into the result we had before we had Q. Sorry, okay, I'll make it clearer. Sorry, we had two. What we had before was this. So now I just plug in our result for Q enclosed. So we get this. And actually, the Q was negative. So we get this over this. So now I can cancel out the lowercase r's are the same lowercase r's. So I could say at the end of the day this, and when we're just about done, I can say this. We have 2 more minutes. That's the magnitude. Our final result. I'll go back to this page in a second. I'm just going to write our final result. If you want a vector, our final result is this. Whichever you prefer, but there's definitely a negative sign in it. Here, I'll stay on this page for a second. We have like 1 minute. First of all, just notice what we just did was we used flux result to eventually say field times area equals charge enclosed over a constant. And we divided both sides by the area to get field. That's ultimately what we just did. We used the flux integral to not have to do any integration at all. We had to choose an appropriate shape. If we had chosen an irregular shape, the whole bottom line is this: the law would still be true if we had chosen a cube, but the E couldn't have come out of the integral then. We would have to literally do an integral, and then there'd be no advantage of any of this. We could have just integrated Coulomb's law. It'd be an impossible integral. So we chose a sphere not to make Gauss's law true, but to make it useful. We chose a sphere, which meant two things. One, we could take the E out of the integral and never actually have to integrate. And two, because we knew the surface area of a sphere and the volume of a sphere, we could then ultimately just say field times known surface area equals charge enclosed, divide both sides by the known surface area, and get an answer to something we've never done before. We just got that field at R, and this is the last thing I'm going to say, is, notice, is a field at R is negative times a constant times R itself. Meaning, this is the last minute, meaning that in this ball of charge, as you get farther and farther away from the center, you experience a stronger and stronger field. You experience a field that is linearly dependent on your distance from the center. In general, if you just walked away from a point, the field would get weaker and weaker, inverse R squared as you walk away. But if you're in the middle of a ball of charge, or if you apply this to mass and gravity, if you walked out from the center of the Earth, farther, as you walk farther and farther away towards the edge of the Earth, what this shows is that the gravitational field you'd experience would get stronger and stronger. If you walk to half the radius of the Earth, you'd experience a gravitational field of 4.9 meters per second squared, et cetera, et cetera. It's saying, so it's a new result. And we only could get something of this nature because of the advantage given by Gauss's law. That's a lot for today. It's a lot. I'll either post tonight or tomorrow. I'll hang out for a second. You guys are doing great. You're all gonna be fine. I will stop. I'll post all this, and I will hang out for any questions or concerns. But thank you all for being you. Okay. Thank you. Okay. Thank you. I'm stopping.